Let's talk about the spring forces first. What is a spring force? So let's start with the spring force. What is a spring forces? So how the spring is going to be applied the force that we are going to be learned. Okay. So to understand that, so let's suppose that we have the spring right now. So right now, this is its natural length of the spring. So this is, you can say, some kind of the equilibrium condition. So for that one, so right now, if I apply the force on this side, so if try to express it, so there is a change in the length. The length have to be changed of the spring. So if initially it is very easy for me to basically to displace the spring, but as you displace it more and more, it become more hard for me to pull it. So this thing is the spring force is changing. Means basically as the displacement is more, so the more spring force will be. So in this case, you have the more, so the spring force, it is directly proportional. You can say if you have the more force applied, so the more spring force is applying to that. So as we have the more displacement, so it is directly proportional. So when you try to pull it, so if I to try to show to you, so let's suppose that, so this is the, right now, this is, we call it equilibrium, where the net force is acting on the system is zero. This position is the natural length of the spring. It is not even compressed, even not is stretched. Okay. So right now, this is the natural length of the spring, we call it. There is no any type of the energy gets stored into the spring right now because it is not stretched. Right now, this position, we call it equilibrium position. This is, we call it equilibrium position. We call it equilibrium position, right? So this is equilibrium position where the net force is zero. Now, let's suppose that I pull it. Now, as I will stretch it, the spring, look at the how the spring force is acting. Displacement is happening on the right side to me, and the force, that is the red arrow that they shown it over there, the displacement is the green one. So you can see as I apply the more displacement I do, the spring force is just in the opposite direction and is directly proportional. If you apply the more force, it is directly proportional to that. So this is, we call it Hooke's law. Simple. And so this is the spring is applying the opposite to the displacement. The direction of the displacement is just opposite to the force, or you can say the spring force is just opposite of the applied force. Correct. So if I look at this carefully, so I mean to say that you, when you apply this one, so if I stop it here, I applied from my hand. This is the force applied by me. The force applied by me is on the right side, and this is the spring force. This is the spring force that is dragging it on the left side of that one. This is the displacement is on the right side where the applied force is. So this is the displacement is on the right side. And as I apply the more force, the spring is going to be applied the more force in the opposite direction to that. According to Newton's third law, even you can think like this. Whatever that the force applied, action that you done, there is a reaction in the opposite side. It is equal, what opposite. So, okay, so that is the force you applied in the block and the spring. So the spring is going to be attracted in the opposite direction to the block, or this is the way that you can think it. So same amount of force. I had to, whatever that I apply to this side, it is the same force on acting on this side. So Now, the thing is, so it is directly proportional, but with the negative. But is it, they are always means exactly it is 52 meter. This is also 52 Newton. That is, it is not actually always, it is directly proportional. If I, this depend upon that one. So if I try to simplify right now, so, so if I take the screenshot of this one to demonstrate to you, because right now, this is the condition that we have it. So this is the equilibrium position. From the equilibrium position, you displace it. So this is the displacement. I'm going to call it, this is the displacement that we have it. So if you look at this carefully, the spring force, the force applied by the spring is directly proportional to the displacement. And whenever in the physics we remove the proportionality sign, there is a some constant. So I'm going to call it the spring force is kx. K is some constant. I will come to that point. But before that, we are missing something because they are displacement and the force are just opposite of each other. So I had to put the negative sign because the spring force always act opposite to the displacement. And what is that? K is actually, K is, we call it spring force, a spring constant. Sorry, this is, we call it a spring constant. This is spring constant. It depends on the spring to spring. So some spring are not too tight, or it is they are easy to pull it. You can think like this. This is pretty hard, I would say. I had to do much the force I had to apply that one. But if you've seen as comparison to the, have you seen in the motorcycle or the cars and something in the trucks, those springs are, their spring constant are very high. Basically, even you can't pull it easily with the hand and something to apply the force and something, because they have the more applied force, you require the more applied force to pull it or to do the expansion. So if I to change the k value here, the k value is now 1. That's fine. So if you change the k value, you can see the force value is increasing because it is just a constant. It depends on the spring to spring. If you change the k value, you can see the, it become more thicker, more stronger, you can say. It is going to be applying the more force in the opposite direction to see that. So this is how you can look into the things are. So this is how the spring forces. This is a spring force. This is the spring force equation. This is how you can demonstrate that one. K is the spring constant. If you have to find it out, the K value, this is just a ratio of the force applied by the spring divided by the displacement. How much the displacement? I'm talking about this x value. Okay, this is the change in the displacement, by the way. This is the change in the displacement that we have it, and we just divide with that one and to get that value. So this is just a ratio, and if somebody asks you the unit for that, this is a Newton per meter. Newton per meter is the constant of this, and this is how. Now let's try to find out the work done by the spring. Just think it like this. Okay. So let's demonstrate that. Okay. So let's suppose that right now you are pulling it. Okay. So let me decrease the k value. Okay. So let me make it 1. And let's go with the 1. Okay. It's okay. Now, as you apply the force to this, okay. So as you apply this force, you are displacing something. You are doing some work. So what is the work done, by the way? Done by you, how much the force applied into displacement. How much the displacement that you had done it. So that is the work done by you. And that, if you look at this carefully, this work is done by me is get stored at this point. So if I click it here, if you look at this carefully, this to displace this one, I had to do some work. That is work done by me. That is the work done on the right side that I done it. That gets stored into the spring. That gets stored into the spring. Just like this, when you pull at anything to the ground, some energy gets stored at from, because so this is, we call it gravitational potential get stored, that is mgh. In the same way, some energy gets stored, and that is the work done by me. In the same way, so when you apply the force to this, you done some work to lift this one, and it gets stored. And as I leave this one, you can see it get converted to the kinetic energy. So some energy gets stored into the spring, and how much that spring energy is, that is only that we are trying to find out. That is the stored energy into the spring. So this is, we call it elastic potential energy, or energy stored into the spring. So what is that is? So elastic potential energy, or energy stored into the spring, uh, elastic potential energy, how you can calculate that one. So can I say like this? The the energy stored into the spring, so that elastic potential energy stored into the spring, elastic potential energy, I'm writing elastic potential energy stored in the spring is equal to how much the work done by me, correct? So that is equal to the work done by me. So how much the work I'm going to do? First thing is, this is the work done by me, or work done to displace that, or the work done by applied force. How much this will be? So, so let's suppose that for consideration. So let's do that, because the force is variable right now. Be careful. So as you displace this one, let's suppose you change the displacement by something. Okay, so you displace it. So this is x displacement, you done it. The spring force is just opposite direction, because that is gravitational potential. This elastic potential will come out to be negative. Let me. The spring force is just the opposite whatever that you apply. Let's suppose you apply the 20 Newton here. The spring force is also 20 Newton, but it's in the opposite direction. So I'm putting it this work done. So the spring force is just opposite of that, but equal. So right now, you can say whatever the work done by me, the spring force is going to be do the same amount of work, but in the negative direction. First, let's calculate this one. It is negative sign come out to be. So right now, because the force is variable, so whenever the force is variable, we had to be write work done as an integration of force. I'm writing, because the force is a function of the x, because as the displacement is changing, the force is displacement into delta x, correct? So I'm going to integrate that. So let's suppose that I integrate from x1 to the x2, means that from the initial position from x1 to x2, this is the limit that I'm putting it. You're doing the work to displace it. Let's suppose from here, so let me call it this position is x1. Let's call it this position is x1, and let's suppose I pull it like this more. So, and this is the initial position x1, and this is the final position x2. So during that, how much the work done by me, that is going to be stored as a spring potential energy. So how much that one will be? So if I had to integrate this one, so let me raise this one. So I can put the negative sign if I had to find out the work done by spring. Right now, work done by me, so that is get stored. So I can put it the negative sign, because this is just the opposite of that one. The spring force is kx, just right now that we discuss this one, x1 to x2, because this is just the opposite of that one. So the k is just a constant. The whatever the integration rule is x power n dx. What you have to do is you have to increase the power by 1, n plus 1 divided by n plus 1 plus c. Plus c is when there is a no limit. If there is a limit, you're not going to be put any kind of the arbitrary constant over there. and you have to increase the power divided. If there is no power, means not visible, it means there is a 1. So you have to increase the power, it will become 2 divided with the 2, and it is nothing but x1, sorry, x1 here, x1 to x2. So I'm going to put it half outside, k, then we put it upper limit minus lower limit, because 1 by 2 I had taken it outside. So this is the work done by a spring, or that gets stored into the elastic potential energy of the spring. So, and if I had to write like this, so this is the work done from displacement from x1 to x2. So this is how the elastic potential energy gets stored into the spring. Elastic potential energy, that much is stored into that. So this is how you can calculate. But remember, sometimes the student do that mistake, so please do not do that one. So sometimes they write like this, kx delta x or x2 minus x1 by whole square. This is wrong. Why? Because this is changed. They are not equal, because x minus y whole square is not this equal to this. They are not equal. Think about this again. You can't write like this. So this is wrong. This is wrong. To say this is wrong. Again, I'm repeating, this is wrong. This you have to write like this only. Or find out the final potential energy minus initial, and this is how you can approach that. Hopefully understood.